Thank you all for attending. I will be representing Iowa State University Rocketry Club. This is our first year competing. We started the club about 10 months back, so it's been a long 10 months to build a 15-foot tall rocket, put it over in the over there. So today I'll be presenting on the non-destructive evaluation of composite materials, specifically the carbon fiber fuselage. Quick preliminary, when I say NDE, I mean non-destructive evaluation. I may also use NDT. So a quick prelim, I'm going to describe what non-destructive evaluation is. It's testing materials or validating materials without breaking them. So we can have a probability of something breaking, or we can know if it's going to break because it has a defect. Several techniques that you may be familiar with is X-ray, radiography, or visual. Visual, you could be just looking for cracks or looking for discoloration on a rocket body. It's non-invasive, so you can see inside the material. Several defects, such as carbon fiber, have defects internal in nature. So those defects need to be discovered if you're going to launch a rocket to 10,000, 30,000 feet. Another quick preliminary before we get into air-coupled ultrasonics, we're going to do ultrasonics. So ultrasonics is using high-frequency sound energy to penetrate into material and get that feedback. So if you can imagine sitting in a pool, throwing the ball into a pool, and someone standing in the middle, those waves are going to reflect off of him before it hits that back wall. So if we can see the picture on the right, that's what we will be seeing on our screen, is the initial pulse, and then the ring down between 0 and 1. The crack echo, you can see on the right, is what we're going to be looking for. And then the back echo surface. So if there's a defect, that back echo surface is going to decrease, and that crack echo is going to show up. If that shows up, that means there's a defect. So this can also be used to characterize materials. You can figure out what materials you're testing. Say you don't know if this is steel or aluminum or copper. You can put a probe to this and find the distance it takes, or the time it takes to travel that distance, if you know the thickness of the material, and you can characterize any material you want. So air-coupled ultrasonics. With ultrasonics, you need a couplant, such as a liquid. Some people use syrup, actually, for a couplant. For air-coupled, it's better because you can automate this process for large surfaces, such as for SpaceX's new carbon fiber fuel tests. The issue with doing regular ultrasound on carbon fiber is that the attenuation in composites, due to attenuation in composites, the ability to extract reflection signals, which is hitting the crack and then bouncing back, is diminished. So we can't detect it. So we have to use a pitch-catch method, which is we're going to send out a sound wave through the composite material and then receive it on the other side. So with that, we can detect dry patches, such as insufficient epoxy. We can detect foreign objects, such as paper, during the manufacturing process. Also, we can detect delaminations. And this can also be done as a way to reduce maintenance costs, or even eliminate sometimes. Because if you can imagine an engine going 250,000 miles, some are going to break down, or even most of them are going to break down, but some are going to reach 500,000 miles. So if a defect is not occurring in that 250,000 miles, there's no reason to throw it away. So you're saving money in the long run. We use a 500 kilohertz transducer, so the higher the hertz, the more accurate the reading will be. And then we used a robotic scan up and down. We measured about 4 inches squared at each time. And with that, we can localize any defect. And if we localize any defect and find it, we can go back and quantify that defect, figure out if this is actually going to have a structural impact on the carbon fiber fuselage. So describing the rocket real quick, we're going to have the thrust plate at the bottom. That's going to experience all the load of the solid rocket motor. So it is important to measure any delaminations, any defects throughout this bottom part. This bottom 5 feet of the 15-foot tall rocket. We can move on to the next one. So, back real quick. So in this method, we used land wave. Land wave is sending a wave through the surface of the material. You can see the red probe, which is the transducer, and then the blue probe, which is the receiver. So what's going to happen is it's going to send, if you can imagine, a speaker and a microphone. It's going to send a wave into the material. It'll translate through it and then come out to the receiver. Once it gets to the receiver, it has a very low acoustic impedance. So that means we have to have nice equipment as well as increase the amplitude or the decibels when we are interpreting this data. And then once we localize the defect, we can use through-wave transmission. So that is, again, sounding the sound through the carbon fiber. If there are any defects, it's going to change that signal. Through that, if we find anything that has any delta change, then we can compare it to an engineering defect comparison. So we would have a good copy of a carbon fiber, and then we have a bad copy, such as one that has poor resin or has a delamination. Next one. And then right there is what we're going to look at if you look at the right picture. So the back is just noise. When we're sending a wave through, it's going to pick up everything. So any sound above what we're using 0.22 megahertz. So anything around that range will pick up, and we want to avoid that. So we set gates. So right in between at that 4 mark is what we're looking at, and any defects means there, or any variations means there's a defect, and then we can compare it to an engineering comparison. So the next one is pulse thermography. With pulse thermography, we partnered with one of the research centers, or the Center of Non-Destructive Evaluation at Iowa State. They're one of the leaders in non-destructive evaluation. With pulse thermography, overlaid it with a 3D image, such as SolidWorks. And this was partnered with Langley NASA, as well as Air Force Research Lab in Ohio. Through this, you can imagine an infrared camera detecting or looking at the test part, and then 2 flash lamps. The flash lamps are basically from an amphitheater. So if you're lighting up a stage, it's emitting a lot of heat. That's what we're going to use. We're going to use large capacitor banks to charge up those and shoot it really fast. With that, you can see on the right side is how it should respond is that black line if there's no defects in the area. If there are, such as a delamination, there's going to be a surface resistance, if you can imagine that, or a contact resistance, if you remember heat transfer. Through that, there will be a shift in the graph or a lower of the graph, depending on what the defect is. So this is the setup. We isolate the test material that we're looking at. Sanding, we have to sand it because we want to reduce reflectivity. We're looking at the emissive rate of the carbon fiber. Looking at the emissive rate through the infrared camera, we need to reduce all other variables, such as reflectivity. If we have a shiny surface, such as a glossy surface, it's going to reflect off of that, and it's going to show up as a bright light, such as if you take a picture in a mirror, it's just going to show bright. With that, we use Data Guzzler, which is just a way of transferring a SolidWorks file into a flat image, and then we set datums on the product or the test subject, so then we can overlay that image. Next slide. So this is the steps of the 3D overlay CAD. First, we have our model from SolidWorks, then we set the data points. Next, we move on to here, where we take the image, and what we can do there is rotate the object, such as in SolidWorks, where we can look everywhere, and we can identify defects. So this is the bottom part of our rocket, the thrust plate will be right there, and if you can see at that bottom side, there's going to be a lighter area, yellow area, in the rest of this area. So that is a defect, that is a delamination that we detected. This, we're able to use certain methods to determine if this would impact the structural integrity and break the rocket. And of course, we don't want that to happen since all the loading is going to be right down there. From this, I worked with some professors to figure out how the fracture mechanics would affect that defect, and if it's going to propagate, or if it's going to stay there, how it's going to affect it, and it was determined it wouldn't. So we passed the product, and it's validated. Now move on to the next. So this is just a basic picture, the 2D image, and we would take 3 pictures of each of the different sides, so then we get that 3D image overlaid. And you can you press it again? I don't know if it worked. Okay, it did. So from there, we can see, say, the direction of the carbon fiber, any delineations, any defects. This can be done after a launch when it hits the ground part. You can hit a rocket. You don't know if you can use it next year. We could do that, or we could test it during the manufacturing process, such as the nose cone. We manufacture nose cone by ourselves, and from there we are able to detect some delaminations as well as issues. And from there we did a second carbon fiber layup to improve the structural integrity and make sure that the nose cone doesn't collapse on itself. So from there, we can move on to questions. So in the design process, it'll be testing. So after the process is manufactured, because non-destructive evaluation is when we're looking at the product. So if you can imagine, you have a factor of safety at 1.75, that's really great. But if you have a defect, then that goes to 0.7, 0.5, and then your rocket's going to fail, even though you have a factor of safety above the requirements. Does that answer your question? Yes, we found a flaw in the bottom of the rocket body fuselage, as I pointed out earlier. Yeah, so right here you can see the orange zone, and then at the bottom part of it we have a yellow area. That is delamination. From there we used fracture mechanics to determine if this is an error. We looked at the radii of the edges of the crack inside of it to determine if it's going to propagate.
You saw that in the model
we tested 2 different areas. So with the radiography, or with the air-coupled ultrasound, we tested that top section with lamp waves. Actually, we did. We used through-wave transmission. So that's 2 probes on either side of the material, and we detected that as well. So we first did the pulse thermography, and then we did the air-coupled valve to make sure that we're not having a false positive, false negative. Yeah, so there are manufactured parts to compare to. We have parts that have, say, not enough resin, so dry spots, we compare that to, and we have a perfect part that we can compare to. It doesn't really matter what the layup is, because we're looking for variations in the signal. So say we have a simple sine wave. It's not going to look like a sine wave, let's just say it is. With that sine wave, if it changes, if the amplitude decreases or increases, that means there's defects. From there, we can go back into it. With air coupled, the 2 probes, if this is, say, a 15-foot diameter fuselage, we can set them, all the way on the opposite sides of each other and then measure it. But that decreases the localization of those defects. So that's why we reduced it to about 4 inches squared. If there are any defects, then we would go back and look at that specific area and determine if there is a delamination, where it is, what can we do. Yes, so we can detect interior part, so just paper when you're doing the layups. We can detect the thickness of the material. So say if it varies, you did a poor layup with a poor female part, you cut it out wrong, you pushed it in, you dropped it, the mold. From there you can see how thick the material is as well. So there, on the nose cone, there were delaminations on the edges of the cone. So we used two similar, or what is it called? So we made it to semi-circles together. From there, we put resin on each side to connect it. We also noticed that there were delaminations on the sides where if you have a female mold, it's right at the edge. And we missed some resin there. So from there, we then did internal layups on the inside to further increase the structural rigidity of the rocket. Safety. Right? And then this is a quick video of well thermography. It is very quick, if you want to press the... Yeah. Or not. Well, it goes over like not even a fraction of a second. It is like 1,500 watts that is released within, again, a fraction of a second. And from there, it adds about 2, 3, 4 Celsius of heat, and then we watch it cool off. So, yeah, that's it.